Okay, vapor pressure and dynamic equilibrium. We've talked about liquids evaporating. Most have been talking about water. We had a beaker, and we talked about molecules escaping. Now let's see what happens if it's not an open container, but it's a closed container. So here we have an Erlenmeyer flask, and instead of it being open to the atmosphere, there's a rubber stopper preventing anything from leaving. So initially, there's evaporation, right? Some of these molecules have enough energy to escape into the gas state, and when they get to the surface, they can do that. There's no gas molecules up here, water molecules anyway, to condense in the beginning, right? So there's no condensation, there's only evaporation. As evaporation proceeds, we get more water molecules in the gas state. These are going to bounce around like gas molecules do. Eventually, they're going to collide with the surface of the water and become trapped. They're going to condense. The rate of condensation depends on how many gas molecules are in that space. The more gas molecules there are, the more gas molecules will crash into the surface of the water and condense. The rate of evaporation is going to be constant. The temperature is the same, the surface area is the same. So we've got evaporation just going on and going on. The condensation, though, is going to increase as the amount of gas in the molecules in the gas state increases. Eventually, we're going to get to a point where the rate of evaporation is equal to the rate of condensation. And at that point, we have what's called a dynamic equilibrium. It's dynamic because molecules are doing things. They're evaporating and they're condensing, but it's an equilibrium because overall, the number of gas molecules is the same. They're changing who they are, but the number is the same. It's a little bit like a busy airport in the middle of the day. You've got planes bringing people in and people leaving on planes. And you've got people going off in cars and taxis and buses and people coming in. And so you've got this constant inflow and outflow of people. But if you took a snapshot every hour, you'd probably see that the number of people in the airport is roughly the same. But it's not the same people. You get the idea? So we've got these gas molecules here in a container. Are those going to exert a pressure? Yeah, gas molecules exert a pressure, right? The pressure of a gas comes about when they run into the walls of the container. So here we have gas molecules. They are going to exert a pressure. So the rate of condensation depends on the number of gas molecules, but really it's more the concentration of gas molecules. We don't usually talk about a concentration of gas, but you could. You say, well, how many gas molecules or how many moles of gas are in this volume of gas? But we usually measure that as a pressure. So these molecules are going to exert a pressure. Any questions yet? So dynamic equilibrium occurs when the rate of condensation equals the rate of vaporization. So here's a graph showing rate increasing up and time increasing as we go to the right. So at time 0, you've got an empty container, you put water in it, you stopper it. There's no water in the gas state. Evaporation begins and remains, the rate of it remains constant because the rate of evaporation depends on the temperature of the water and on the surface area. And neither of those is changing. So rate of evaporation is just constant. The rate of condensation starts out at 0 because there's nothing up there to condense. As evaporation proceeds and we get more gas molecules, then the rate of condensation increases. And that will increase until those two rates are equal. And then they'll just stay at that level until something changes. So that evaporated substance in the gas state exerts a pressure, and we call that the vapor pressure. It's the pressure of that substance over its liquid. So the vapor pressure is going to depend on the strength of the intermolecular forces that were holding that substance together as a liquid. Because if the intermolecular forces are weak, then more of those molecules are able to escape under any given set of conditions than if the intermolecular forces are very strong. And so you'll end up with more molecules in the gas state, and so the vapor pressure will be higher. Something with very strong intermolecular forces is going to have a very low vapor pressure. That make sense? It's so quiet. Have you guys heard of Le Chatelier's principle? No? So Le Chatelier was a French scientist, as you can kind of guess from his name. And he studied equilibria. So this idea that he came up with is that if you have a system in dynamic equilibrium, so you've got a forward process and a reverse process. Here we're talking about evaporation and condensation, but it could be a reaction. It can be lots of different things. So it's in equilibrium. If you disturb the reaction, if you disturb the system in some way, the equilibrium will shift to undo what was done to it. I like Le Chatelier's principle because I'm one of those people who does not like change, unless it's my idea. If I decide I want to paint the living room a different color, then change is awesome. But, if someone decides to cut down the dead tree outside my office window, I don't like that, right? I know it was dead, but it was the tree outside my window. They did that over the weekend. I don't like change. So I fight against it. I resist it. A dynamic equilibrium will resist change. So here we have a movable piston, and we've got, it looks like probably pentane in here. We've got a liquid and its gas, vapor. They are in equilibrium. They've been in this container long enough that we've got rate of evaporation equal to rate of condensation. And so it's all nice, balanced. If we pull up on this piston, we're going to increase the space that the gas is occupying. If we think of concentration of gas, you've got the same number of molecules up there, and you're increasing the volume. What does that do to the concentration? It decreases the concentration. So what would that do to the rate of condensation? The rate of condensation would go down, right? Because now these particles have more space to bounce around, so they're not going to run into the surface as frequently. Rate of condensation is going to go down. But the rate of evaporation is just going to keep chugging away because the space above the liquid does not affect the rate of evaporation. So what's going to happen is the system will keep evaporating to restore that concentration of gas. Of course, we don't talk about the concentration. We talk about the pressure. The pressure of a gas is proportional to its volume and to the number of moles of gas, right? So here we have a vapor pressure. Here we're increasing the volume, which decreases the pressure of that gas. The system will shift and will continue to pump out more gas molecules to restore the vapor pressure. Does that make sense? So you decrease the pressure of that gas, and it says, hey, wait a minute, we had this all set up. This vapor pressure is supposed to be X. So you messed with us, now we're going to fix you, and we'll get back to that same vapor pressure. Doesn't matter what volume you make this, the system will shift around. If we decrease the volume, we concentrate, we push these gas molecules together, that's going to increase the rate of condensation, while the rate of evaporation continues to be the same. And eventually those rates are going to become the same, and you're going to end up with the same vapor pressure. That make sense? So no matter what you do to it, the vapor pressure is going to be the same. The vapor pressure depends only on the temperature of the liquid, because the temperature of the liquid affects how fast the particles are moving. And the faster you run at the red rover line, the more likely you are to be successful So increasing the temperature increases how fast the molecules are moving, more of them can evaporate. But doing anything up here to the volume is not going to affect the pressure at all. It will temporarily, and then the system will recover. Any questions? There's a temperature dependence of vapor pressure. So the vapor pressure will increase as the temperature increases. Because as you increase the temperature, more molecules are able to escape, and so the rate of evaporation will increase. That's going to cause the vapor pressure to increase as well. So we see that small changes in temperature can have large effects in the vapor pressure. So this red line is of particular interest. This is water. Water is very low vapor pressure down here, and as you increase the temperature, it gets larger and larger and larger. Up here, the vapor pressure is going to hit 760 torr, which is 1 atmosphere, at its boiling point of 100 degrees Celsius. Don't know what else to say about that. These are not linear relationships, though. They're curves. They're exponential. So the boiling point of a liquid is the temperature at which the liquid's vapor pressure is equal to the external pressure. So if we go back here, you increase the temperature of water and the vapor pressure increases. When you get to a vapor pressure equal to the atmospheric pressure, the water begins to boil. And so for ethyl alcohol, that's going to happen at a lower temperature. For diethyl ether, it's going to happen at an even lower temperature. And that's due to the strength of the intermolecular forces. So here we have an illustration of what's going on with water boiling. When the vapor pressure equals the external pressure, then the molecules, even in the inside of the liquid, in the interior, not just the ones at the surface, but the ones in the interior, have enough energy to go into the gas state. And so they form pockets of gas inside the water. And of course, those have low density, and so they come up and they are released into the space above. But that's what those bubbles are. Those are water in the gas state. And they tend to happen at the bottom in a situation like that, because where's the heat coming from? The bottom. And so it's probably going to be a little warmer at the bottom of that pot. And so that's why we tend to see the bubbles form at the bottom. So the boiling point is going to change if we change the external pressure. So do you know what a pressure cooker is? Yes. So a pressure cooker is a pot that has a lid that clamps on. And it's usually got some sort of a pressure gauge and a safety vent. So you put your food in there, and you have to have some water in there, and you heat it up. As you heat up the water, and the water evaporates, the pressure begins to build up. Okay? But the water will not boil until the vapor pressure is equal to the external pressure. Because we've got a clamped-on lid, the pressure will go higher than 1 atmosphere. What happens here is at atmospheric pressure, open to the atmosphere, water will boil at 100 degrees, and it'll stay there. If we put pressure on this, like here's 800 torr, up here's probably 1,000 torr. If we have higher pressure, then the water's going to boil at a higher temperature. The reason that a pressure cooker cooks food faster is because when you allow pressure to build up, then the water will boil at a higher temperature. If it's open to the atmosphere, water boils at 100 degrees Celsius. It doesn't matter how high you turn up the burner, doesn't matter how long you let it sit there, it's going to be 100 degrees. Food cooks faster when you fry it because oil can be heated above 100 degrees. In a pressure cooker, you can get the temperature higher, and so you can cook the food faster.
So the limiting factor in cooking food is how hot
Yeah, a limiting factor in cooking food is how hot can you get it? right? On the stove, if you've got water, it'll boil and then it'll maintain its temperature. Now, if you're pan frying a steak, that'll be hotter than 100 degrees Celsius. But if you're doing anything in water, it's just going to level out at 100 degrees. So we define a normal boiling point. Normal is referring to, this is the boiling point at atmospheric pressure. This is regular, normal boiling point. You can have a boiling point at other pressures. You can make it boil at different pressures. You can make water boil at a lower temperature. Let's go back to this graph. If I reduce the pressure above the water, perhaps I put it in a big vacuum flask and have a nice powerful vacuum pump and pull a vacuum on this, I can get water to boil at room temperature. I want to get one of these pumps because this is one of my vivid memories from high school chemistry. My professor, well, my teacher, had a big vacuum flask, put water in there, attached it all up, hooked it up to a pump, and then he started his lesson. After a while, the water in the flask began to boil. It's just sitting on a bench, just a black bench like this. It's just sitting there. There's no heat source hiding underneath. The water began to boil. And then he made us all come up and touch the flask. Now, generally, is it a good idea to touch a pot of boiling water? No, you're going to burn your fingers. The first person was pretty scared, right? We all touched it. It was the same temperature as the bench. It was just like, wow. So I really want to do that, but we don't have the right kind of a pump. But you can do that. You've maybe seen on like baking instructions for cakes and things, there's high altitude instructions. That's because at high altitudes, the atmospheric pressure is lower, water boils at a lower temperature, and so you have to adjust the cooking times. Yeah?
So how does water not boil in space? Because there's pretty much no pressure, atmospheric pressure.
Well, I think water would boil in space.
Yeah.
Yeah. I mean, you don't see just water floating around in outer space. No, I think it would definitely go into the gas state. Because you can get water to boil at a very, very low temperature if the pressure's low enough.
Boiling water, zero gravity.
Yeah.
Cooking fish.
Well, the gravity is not really going to affect the boiling. It's the pressure. And so we saw that video of the astronaut, right, in the space station doing funky things with water, right? Because it's like, wow, this is cool. That water wasn't boiling. But what was the pressure inside the space station? It was probably pretty close to 1 atmosphere. Because otherwise the astronaut would have some serious problems, right? And we wanted to keep them alive. So this is what we call a heating curve. So we're looking at the temperature of water as we add heat to it. So you take some water at room temperature and you put it on the stove and you turn on the burner and you heat it up. And you're putting heat into the water, what happens? The temperature goes up, right? So the temperature goes up as we put heat into it. Once it gets to 100 degrees Celsius, the water begins to boil and the temperature stays the same. That's not what you would expect, right? You'd expect, well, if you heat it more, then it'll get hotter. But what's going on here is particles are leaving the water. There's an average kinetic energy, right, based on the temperature. Some molecules are higher in energy, some are lower in energy. Which are the particles that are leaving, the high energy or the low energy ones? The high energy ones. Those are the ones that are leaving. The lower energy ones are staying behind. So as the water is boiling, the particles that have enough energy to escape into the gas state do so, and what does that do to the average temperature? It keeps it the same. We talked about just water evaporating in an insulated container would get colder. This isn't going to get colder because we're adding heat to it. Adding heat to it replaces the energy taken away by the molecules that are leaving. Adding more heat will only cause the water to boil faster. The temperature cannot rise until all of the water boils away. Once all the water is into the gas state, then the temperature of the steam can rise higher. But boiling water will always be 100 degrees Celsius. Yes?
Is there a limit for the temperature of the water vapor?
Is there a limit for the temperature of the steam? I don't think so. There's a limit to how hot we can make things, just, but, if you took it to the surface of the sun, I suppose at some point the water molecules would break apart. Yeah.
Does that factor in everything? So when you're boiling into the liquid, does it have this peak in how hot it can get before it gets bigger? No?
Yeah, this is going to happen with any liquid. So if you're boiling alcohol, which I wouldn't recommend doing, that's also going to have a flat place. Now, when you have mixtures of different liquids, then you have some other things happening. You can distill liquids and separate them based on their boiling points. So, like when they make alcohol, right? You take some organic matter that has sugar in it and you ferment it and you get alcohol, and then there's still water and there's other things in there. And how do you separate the alcohol from the water? Like, how do they make absolute vodka or absolute alcohol? You distill it. They're called distilled spirits, right? So they actually use a still, and you boil the mixture, and the substance with the lower boiling point will leave first, and the substance with the higher boiling point will remain behind. What you do is you collect the vapor as it comes out instead of just letting it go into the air, because it's that lower boiling point stuff, the alcohol, that you want. So you collect it and cool it and condense it, and then the water's left behind and all the solid, junky stuff. And so that's how they separate out alcohol. Okay, so that relationship we saw with these curves. They're nice, pretty curves, but curves are difficult to work with. It's not a linear relationship. It's an exponential relationship. Every semester, I look at this slide and I'm like, dang, I need to fix that. I don't know what happened here. Okay, this is beta times e to this. This is the exponent on e. E is a natural logarithm as opposed to the base 10 logarithm. Beta is just a constant. So if we take that exponential relationship and rearrange it by taking the natural log of both sides, we get what's called the Clausius-Clapeyron equation. So the natural log of the vapor pressure is equal to negative heat of vaporization over R times 1 over the temperature plus the natural log of B. So why the heck would we do that? Well, this is Y. This is the slope. This is X plus B. So we can put it into a linear form that way, Y equals mx plus B. So if we graph the natural log of the vapor pressure versus 1 over the temperature in kelvins, we get a straight line. The slope is going to be equal to negative delta H over R. And so you can graph data, you can measure the vapor pressure at various temperatures, graph the data, and calculate the heat of vaporization for that substance. So you can end up with a graph like this. So natural log of the vapor pressure versus 1 over the temperature. We need the temperature to be in kelvins because if we have a 0 in here and negative temperatures, it's going to mess up everything. So we have to use kelvins here. And so we get a line like this. So this is real data. It doesn't all fall exactly on the line, but we use linear regression and we get the line. So you can get the slope of the line. The slope is equal to negative delta H over R. So that means that delta H is equal to negative slope times R. We want to use the value of R, 8.314 joules per mole Kelvin, because that causes the units to work out correctly, and we end up with heat of vaporization in joules per mole. Yeah.
Will you give us this equation?
I will. So the actual Clausius-Clapeyron equation that we're talking about right now, we're not going to use that on an exam because that requires graphing data, and that's just way too much to do on an exam, right? But I'm going to show you a different form of it that might be on the exam. Did you have a question?
So you have like two P-based things, and it kind of confused me. I didn't get what was the difference of the first one?
Between this equation and this equation?
Yeah.
So here we took, well, let's put it back this way. So here we've got this exponential. And so if we take the natural logarithm of both sides, so we've got the natural logarithm of this, and that's equal to the natural logarithm of all of this, well, that would be the natural log of beta plus this part. So it's just rearranging the equation.
Oh, okay.
Yeah, which is something we do a lot. Anybody else have any questions? So this is a problem that's given in the textbook. I'm not going to do the whole thing because we'd have to pull up Excel and graph it and get to linear regression, and I don't think it's worth lecture time to do that. So how would you approach this problem? It says the vapor pressure of carbon tetrachloride is measured as a function of the temperature. Results are tabulated. Find the heat of vaporization, carbon tetrachloride. So what you would do here is you'd take this data and you have to manipulate it. So you need to find 1 over T. So you need to take all of these temperatures and find the inverse of them. So 1 divided by 200 and write down what that is. 1 divided by 220 and write that down. And then we need the natural log of the vapor pressure. So we also have to calculate the natural log of the vapor pressure. So you'll take the natural log of 0.8 and write that down. The natural log of 4.5, write that down. And then you're going to graph natural log of P on the y-axis and 1 over T on the x-axis.
So our vapor pressure always has to be in torr, not in atmosphere?
To do this Clausius-Clapeyron equation graph, it should be in torr, yeah, because then the units are going to work out. Otherwise, you have to do some funky things with units at the end because they're not going to cancel out nicely. So then you use linear regression and you find the slope of the line. And you could find the intercept, but we really don't care about the intercept. We just want to know what the slope of the line is. So the slope of the line is negative delta H, heat of vaporization, over R. So to find the heat of vaporization is going to be negative M times R. And you use the value of R equals 8.314 joules per mole Kelvin. And so you can calculate it that way. There could be a homework problem like that. I don't remember what's in the homework assignment, honestly. But I won't make you do one of those on an exam. But I want you to be aware that this can be done. Okay? Because how are you going to measure the heat of vaporization? That's kind of tricky to measure. This is a lot easier. Just take your liquid and at multiple temperatures, measure the vapor pressure. And then you can graph it and find this out. Once you set this up in a spreadsheet, like Excel, and have everything fixed, all you have to do is type in the numbers, and the spreadsheet does all the math for you and just spits out the delta H. It's very tedious to set up the first time, but after that, it's pretty easy.
Is R constant?
R is a constant. R is the ideal gas constant, but it's not the 0.08201 because it's 206 because the units are different. So this is more useful for us in Chem 1A. We can express it in a 2-point form, and I'll spare you how you end up with this 2-point form. I will give you this equation on your list of equations and useful information for the exam, so you don't have to memorize the equation itself, but you should know how to use it because pretty sure I'll put one of these on the test. So this tells us the natural log of P2 over P1 is equal to negative delta H of heat of vaporization over R times the quantity 1 over T2 minus 1 over T1. The T's have to be in Kelvin. The pressures here, because it's a ratio of the pressures, as long as the pressures are in the same unit, those units are going to cancel out, and so the pressure unit doesn't matter. It just has to be consistent. So this is useful because if you know the normal boiling point of a substance, that is the temperature at which the vapor pressure equals 1 atmosphere. So there you've got 1 point. And then the other point, say you want the vapor pressure at a different temperature. Well, now you have 2 temperatures, 1 pressure, you can solve for the other pressure. So let's do that. Propane has a normal boiling point of negative 42 degrees Celsius, heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure of propane at 25 degrees Celsius? So this is going to use the 2-point form of the Clausius-Clapeyron equation. So the natural log of P2 over P1 equals negative, try that again, negative delta H over R times the quantity 1 over T2 minus 1 over T1. They're asking for a vapor pressure. What is the vapor pressure? So we can choose which, we've got these 2 conditions, the normal boiling point, minus 42, and we've got 25 degrees. We can choose which of those is 1 and which is 2. It doesn't matter, but it might make the problem easier or harder to solve. So I'm going to choose to call the vapor pressure I'm looking for P2, because then when I solve this, I'm looking for the numerator instead of the denominator, and I'm pretty sure that's going to be easier. So I'm going to call this P2. That's what I'm looking for. That makes this T2, because those two go together, the vapor pressure at this temperature. So that's T2. This needs to be in kelvins. So let's convert that to kelvins. It's going to be 298.15 Kelvin. So then this one must be the other temperature, T1. Can't do that one in my head. I could try, but that'd be ugly. 273.15 minus 42, 231.15. So that's the temperature 1. What's pressure 1? This is the one that stumps students on an exam. They're like, you didn't give me pressure 1. No, this is delta H. We need that here, but we need T1. What does normal boiling point mean? Boiling point at 1 atmosphere. So this word normal tells me that that pressure is equal to 1 atmosphere. Often overlooked fun fact, or not so fun. Well, you could multiply by 760 and turn it into torr, but because this is a ratio, any pressure unit will be fine. It's just that when you find P2, it's going to have the same unit as whatever unit you use, that's way too many U's, for P1. So I'm thinking that P1 being 1 atmosphere is going to make my math pretty simple. Because P2 divided by 1 is just P2, right? So that's nice. So we can plug these in here. let's see, I undid something. Okay. So the natural log of P2, that's what we're looking for, divided by 1 atmosphere equals, negative heat of vaporization is given to us, negative 19.04 kilojoules per mole, divided by that gas constant, 8.314 joules per mole Kelvin, times 1 over T2, 1 over 298.15 Kelvin, minus 1 over 231.15 Kelvin. Before we do all the math here, let's see if the units are going to be okay. Yeah?
Why do you have to include the LN in this?
Because that's a function. It's the natural log of this value.
That's how you got rid of the E.
That's how we got rid of the exponential in the first place.
So if we were solving for like a different number in that equation, would you be able to put a number there, or does it just like stay with the pressures?
This stays with the pressures. So there's log and there's natural log. This is a function, like multiplying or sine or raising to a power. The opposite of this is 10 to the x. The opposite of natural log is e to the x. It's something you did learn in high school, but you maybe set it aside because you haven't used it much since. Okay? Go back and rack your brains, and they did teach you that in high school. I know they did. But it's an excellent question because a lot of students have forgotten what logarithms are, and so they're like, yeah, what is that ln, and what do we do with that? It's not just a couple of letters that we can ignore. Okay, so you just write them down there. So for now, this would be faster. For now, let's just focus on the right side of this and look at the units. So the moles are going to cancel, and these kelvins are going to cancel. What's going to happen with the joules and the kilojoules?
You're going to need to change.
Yeah, we really should change this one into joules.
Oh, okay.
I think that would be easier. So we could do that like this. I'm going to move this over. I'm going to call this joules per mole. And instead of writing the K, I'm going to write what K means, times 10 to the third. That's kind of the shortcut way. The other way, if that didn't make you feel good, just take this and convert it the regular way into joules per mole and stick it in. This is not proper scientific notation, but your calculator will still understand. Okay, so then we have to get this into the calculator. So I've got negative 19.04 EE3 divided by 8.314 times, and I'm going to use parentheses, times the quantity 1 divided by 298.15 minus 1 divided by 231.15, close parentheses, equals. It's not negative, though, because there was a negative sign in the beginning. So it should be 2.22.
Oh.
Let's just call it 2.2264. My joules canceled out. What are the units there? There aren't any units. They canceled out. So this is just a regular old number there. If we look at this, the natural log of P2 dividing by 1 is still P2, right? The natural log of P2 equals 2.2264, which is all very nice and everything, but that doesn't tell us what P2 is. To get P2, we have to undo this function. So if we're multiplying, we divide, but this is logarithms, so we do the anti-log. The anti-log is e to the x. So we're going to take e to the x of both sides. So e to the natural log of P2 will equal e to the 2.2264. E to the x and natural log are the opposites of each other, like matter and antimatter. They cancel each other out. So that says that P2 equals e to the 2.2264. So you have a button on your calculator that will do that. It might be on the ln button as another function, or on my calculator, the 36X Pro, it's with the 10 to the x button. So I do e to the x, gives me a little box, and then I type in the 2.2264, and press equals. And I get 9.2664, a whole bunch of stuff after that. Make sure that you can get your calculator to give you that number. What's the unit on P2? Atmospheres. So here we had P2 over P1. Those have the same unit. Since the denominator was atmospheres, then the numerator is atmospheres.
You would divide that 9.266 times divided by 2 if the atmospheres were 2.
Okay, that's a good question. So what if this was 2 atmospheres instead of 1? You would not take this 9.2664 and divide by 2. No. So how would you do that? You'd have natural log of P2 over 2 equals some number. So when you did e to the x, you get P2 over 2 equals 9.2664. So you'd actually multiply by 2, not divide by 2. So this is a what if, not part of the actual problem, but a good what if. Any questions? Anytime you're dealing with logarithms, sig figs get a little wonky. It is always, always, always better to include too many significant figures than not enough, especially when you're taking logarithms, because actually the numbers before the decimal point are more of a place-holding zero kind of a thing, and it's the numbers after the decimal point that give you the sig figs. So if you round this off too much, you can end up with a very, very different number. So just be careful of that.
Or if you forget the negative, it gives you.
Or if you forget the negative, then things get all crazy screwy. Yep. Okay. So what if we're vaporizing that liquid in a sealed container and we're heating it? What's going to happen? Well, as the temperature goes up, the pressure goes up as well. So here's a window into a container where we can have high temperature and high pressure. So initially we see there's a liquid and there's a gas. As we continue to heat this up, the gas becomes more dense, the liquid becomes less dense, they become more like each other, and at the critical point, they merge into one state. You don't have a gas and a liquid anymore. You have one state, and it's called a supercritical fluid. Supercritical fluid exists above a particular temperature in a sealed container.
Is it useful in any way?
Pardon me?
Is it useful in any way?
Yes, actually it is. It is very useful. So it's called a supercritical fluid. And we'll get to the use of it in a minute. So that critical temperature is the temperature at which the supercritical fluid forms. Above that temperature, and it's going to be different for different substances, a liquid cannot exist. So the supercritical point, the supercritical temperature for water is obviously above 100 degrees Celsius. I don't know what it is off the top of my head. But it's a high temperature. Can you get water to exist as a liquid at, say, 150 degrees Celsius? You can if you put enough pressure on it. Because as you increase the pressure, you increase the boiling point. And so you can get it to be a liquid at a higher temperature. But there's a limit to that, and the limit is the critical temperature. Above the critical temperature, the liquid doesn't exist and you have a supercritical fluid. That also comes with a particular pressure, and it's called the supercritical pressure.
374 Celsius.
374 Celsius, thank you. So the critical temperature for water is 374 Celsius. You go up to 378 Celsius, you cannot, no matter how much pressure you put on it, you cannot make water be a liquid. You can get a supercritical fluid, but you can't get a liquid anymore. And that's true for most substances that don't decompose. You got a question?
Does it have any uses?
It does. He asked that question earlier, and those are on the next slide. So, and this point here, supercritical fluids are very useful as solvents. Okay, actually it's not on the next slide, maybe it's on this slide. So they use supercritical CO2 to get the caffeine out of coffee, make decaf coffee. Ever wonder, how can you buy decaffeinated coffee beans?
So why does it become blacker?
Why does it become blacker without the caffeine?
Yeah, why
I wasn't aware of that. I thought that had to do with how much you roasted it.
They're duller.
They're duller?
It's dull.
It's really
Okay. So I'm not a coffee connoisseur because I can't stand the stuff. I make it for my husband because I love him and because he loves coffee, but I don't drink the stuff, so I don't pay too much attention to it. But they're telling me that decaffeinated coffee beans have a more dull finish, and the regular coffee beans are kind of shiny and almost oily looking. I do know that because my husband only drinks caffeine coffee. That's the point of drinking coffee, right? So you can imagine making like instant coffee or something and getting the caffeine out of it. But did you ever wonder, how do they get the caffeine out of whole coffee beans? Do they grow a special plant that doesn't have caffeine in its beans? No, they don't. They take the coffee beans and they put them in supercritical CO2. The caffeine is soluble in CO2. And so it dissolves in the supercritical fluid, and that's a fluid and you can wash it away. And then the coffee beans are left. The stuff that gives you most of those good flavors, or to people who like coffee, they think they're good. The flavors and stuff remain because they're not soluble in the CO2. But the difference in the appearance, I'm guessing, is that there is some component that makes the regular coffee beans shiny that does get taken away by the CO2. And the nice thing about this is, so you treat the coffee beans like this, and then you take them out of the container, and do you have any harmful chemical solvent residues on the coffee beans? No. As soon as you take it out of that pressurized container, it goes back to CO2, it evaporates, and it's gone. It's not polluting the atmosphere, it's not leaving toxic stuff on your coffee beans.
Have to be heated up to supercritical liquid.
You would have to heat them, yes. Now, the supercritical temperature, the critical temperature for CO2 is lower than for water. So, because if it was too high, it would destroy the coffee beans and that wouldn't work. And supercritical fluids are used as solvents in lots of different situations. This is just one that appeals to students. So that's why we tell you about it.
31.10 Celsius.
31 degrees Celsius. Okay. So the critical temperature, 31 degrees Celsius. So that's not much above room temperature for CO2. In fact, that's below body temperature. Your body is at 37 degrees Celsius. So you can use CO2 to decaffeinate the coffee without essentially roasting the coffee and doing other things to it. No, you can't roast it in your hands.
Does Does the supercritical fluid have different properties of matter? Like,
It has different properties than either a gas or a liquid. So it's between them. It's a very, very weird thing. And the more you study science, the more weird things you learn about. Kind of just... And sometimes, I mean, for me, some of those things, it's like, okay, you told me about them. I don't like that. I'm just going to choose not to study that area. You know, the guys that came up with quantum mechanics didn't like it, right? Well, there's nobody forcing you to continue studying it, but, you know, they were curious, so they went on.
Why didn't they like it?
They didn't like it because it didn't make any sense. It just seemed wrong, but they couldn't disprove it. So they just kept trying because they didn't like it.
So it was right.
Pardon me?
Was quantum mechanics.
I